Hi friend, welcome to the abstract algebra class. It is class 78. In this class we will prove a theorem about cyclic group, uh, order of cyclic group. Here is the statement of the theorem. The order of a cyclic group is equal to the order of its generator. The order of a cyclic group is equal to the order of its generator. It is clear. Now we want to prove this theorem. Let G be a cyclic group generated by an element A, that is G is equal to e to the power n belongs to Z. Now we have to prove that order of G is equal to order of its generator. Here A is the generator of G. Case 1, let order of A is equal to n. N is a finite number. N is finite number. Then a to the power 0 is equal to a to the power 1, a to the power 2, and so on, a to the power n plus 1, all belongs to G. Because A is generator of G, G is cyclic group. We now prove that all these elements are this thing, and these are the only element of G. Actually, if we want to prove that G is a cyclic group of order n, then we have to prove that all of these are belongs to G and they are distinct element. The only distinct element of G. Let I comma G are any two positive integers such that a to the power I is equal to a to the power j. We assume that they are not distinct, for I is not equal to j. I comma j less than n, I comma j less than or equal to n minus 1. They are not equal to n. N is the order of element A. Since I is not equal to J, this implies I greater than J or I less than J. It is the order of the order of I and J. Take I is not. First we assume that I is not I greater than J. A to the power I is equal to a to the power J. This implies a to the power I. We multiply both sides by a to the power minus J. Then we get a to the power I minus j is equal to a to the power 0, it is equal to e. E is the identity element. A to the power 0 is equal to e. This implies order of A is equal to I minus j less than n. If we have a to the power n is equal to e, then n is the least positive integer, or n is order. But here a to the power I minus j is equal to a to the power 0 is equal to e. That means order of A is equal to I minus j. It is less than n. It is not equal to n. I greater than j. This implies I minus j also greater than 0. This implies I minus j less than n. This is a contradiction. Therefore, I is not greater than j. Similarly, I is not less than j. This implies I equal to j. This implies a to the power I is equal to a to the power j, or a to the power I is equal to a to the power j if and only if I is equal to j. Therefore, a to the power I is not equal to a to the power j if and only if I is not equal to j. Since a to the power 0, a to the power 1, and so on, a to the power n minus 2 are distinct element of j, we prove that they are distinct element of j. Let a to the power p is an element belongs to G, where P belongs to Z. P is an integer. By the division algorithm, there exists Q or belongs to Z such that P is equal to n to the power n into Q plus R. R is equal to 0 or R equal to less than n. Now a to the power P is equal to a to the power n into Q plus R. It is equal to a to the power n into Q into a to the power R. It is equal to, we can write a to the power n whole to the power q into a to the power r. It is equal to, instead of a to the power n, we can write e to the power q into a to the power r. It is equal to a to the power r. Therefore, here a to the power p is equal to a to the power r. R is equal to 0 or r is less than 1, n. Therefore, a to the power p is one of the element among a to the power 0, comma a to the power 1, a to the power 1, so on, a to the power n minus 1 belongs to G. Case 2, let order of A is infinite. Let m comma n are any two positive integers such that m greater than n. A to the power m is equal to a to the power n. This implies a to the power, we assume that a to the power m is equal to a to the power n. This implies a to the power m into a to the power minus m, it is equal to a to the power n into a to the power minus n. Both sides multiply by a to the power minus n. This implies a to the power m minus 1, it is equal to a to the power 0. This implies a to the power m minus 1, it is equal to e. This implies order of A is equal to m minus 1, m minus n. M minus n is a positive integer. This implies order of A is finite. This is a contradiction. Therefore, a to the power m is not equal to a to the power m. Therefore, a to the power m belongs to G for infinite value of m. Therefore, order of G is for infinite. From case 1 and case 2, we get order of A is equal to order of G, which is the proof the statement of the theorem. Here is another theorem. If G is an infinite cyclic group, then G has exactly two generators which are inverse of each other. If G is an infinite cyclic group, then G has two generators which both of them are inverse of each other. We want to prove this theorem. First we analyze the theorem. Let G be an infinite cyclic group generated by an element A, that is G is equal to a to the power n such that n belongs to Z. It is the definition of cyclic group. Let a to the power m is also a generator of G, that is G is equal to cyclic group which is generated by a to the power m. Since A belongs to G, it is equal to a cyclic group a to the power n. Then there exists an integer p such that A is equal to a to the power m whole to the power p. This implies A is equal to a to the power m into p. Multiply both sides by a to the power minus 1, we get a into a to the power minus 1 is equal to a to the power m n into p into a to the power minus 1. A into a inverse is equal to e. E is equal to a to the power m into p minus 1, where e is an identity element in G. Therefore, a to the power m minus 1, m p minus 1 is equal to e if m minus m into p minus 1 greater than 0, then there exists an integer q belongs to Z such that q is equal to m into p minus 1. Q is also an integer. This implies a to the power q is equal to e. This implies order of A is equal to q. According to the definition of order of an element, we can write order of A is equal to q, a finite number. This is a contradiction since order of G is equal to order of A. This implies order of A is infinite. Order of A cannot be finite. Therefore, this is a contradiction. Because order of G is equal to order of A. Therefore, order of A is infinite. Hence, m into p minus 1 is equal to 0. This implies m into p is equal to 1. There is some possibilities. M comma p belongs to Z. This implies m is equal to or p is equal to. Or we can write m is equal to minus 1 or p is equal to minus 1. Therefore, if we take the first element of m is equal to 1 from here and m is equal to minus 1 from here, we get m is equal to 1 or m is equal to minus 1. Since G is equal to the cyclic group a to the power m generated by a to the power m, this implies G is equal to cyclic group which generated by A. If m is equal to 1 and G is equal to cyclic group which generated by minus 1, if m is equal to minus 1. Here m was equal to 1, but Another possibility is exists G is equal to a to the power minus 1 if m is equal to minus 1. G is an infinite cyclic group generated by A or as well as generated by A to the power minus 1. Here is another also here. Here is two cyclic group which is generated by here generated by A and here generated by minus 1. Hence we get we prove the statement of the theorem. Every infinite cyclic group has only two generators which they are inverse of each other. Hence the proof of the theorem.